Hi and Assalamualaikum. My name is Nur Aishanti Rasul. So now I will like to present for the introduction part. So our project focuses on the designing microwave filters using the insertion loss method. So the microwave filters are important in RF communication system because they allow desired frequencies to pass while rejecting unwanted frequencies. So this filter are widely used in wireless communication, satellite system, radar, and IoT applications. In this project, we are given two tasks to design, which is the first one is low pass filter, and the second one is the band pass filter, and verify their performance using ADS software. So the insertion loss method, the main design technique used in the insertion loss method, this method uses filters, specifications such as ripple and attenuation to determine the filter order and component values. So it provides a systematic approach to achieve the required frequency response. So the second one is the Richard transformations. So the Richard transformation is used to convert lump elements such as the inductor and capacitor into the transmission line structures that are more suitable for microwave frequency. So the Kuroda identities. The Kuroda identities are applied to simplify the transmission line network and convert impractical structures into a practical open circuit stub implementations. So the bandpass filter designs is allow only a specific range of frequencies to pass while rejecting frequencies outside the desired band. So it is commonly used in communication system to isolate the required signals. So that's all from me. Next, I will pass to the Nur Zahira to explain the calculation part and design process for the low pass and band pass filter. Thank you.
Hi and Assalamualaikum. My name is Nur Zahra binti Muhammad Mubarak. So today I will explain the calculation and simulation part. So first, for the calculation, we have actually two tasks has given. First is low pass filter and band pass filter. So we need to design a filter based on the criteria that have been given. So for the first task, a low pass filter, we have 2.5 gigahertz cut off frequency, 35 dB attenuation at 3.5 gigahertz, and 3 dB echo ripple. So from this criteria, so first step, we need to find the W over WC minus 1. The value is 0.4. After we get the value, and we as we know 35 dB, so we can identify the end value actually. So for this low pass filter, the end value I get is n equals to 6. It's actually between 5 and 6. So I had take the highest value is equals to n equals to 6. So when n equals to 6, is considered as a even number. So we will design our circuit in T shape. So after we get the n value, so from the 3 dB equal ripple table, so we get the G values, then we can in it into the lump circuit. So this is the T shape circuit. So we start with inductor, capacitor, inductor, capacitor, inductor, capacitor. So after we get this lump circuit, so we want to change into the copper circuit, the copper design. So our main objective of this is to change all into an open circuit. Okay, this is the circuit of low pass filter design in ADS. So this is the S parameter. Use it for the frequency swap. Use it to evaluate and filter performance, especially S11 and S21. Okay, next is the Optim is use it for it will automatically modify the transmission line dimension to achieve a desired filter responsive. And for term 1 and term 2, both are terminated with 50 ohm to match standard RF measurement. So for the MLIN is a section act as a series transmission line. For MTTE is for connecting junction between series and open circuit stub. And for MLOC is a open stub. So how after we finally design our filter circuit, so we can see the output we have at 2.5 giga we get negative 3 dB, and for 3.5 gigahertz we get negative 49. Actually our question give is 35, negative 35, but it's acceptable is more than 35. For the low pass filter, we have seen that we get actually two things to be included in the report. First is the optimized graph and optimized graph. So for the unoptimized, as we can see, we get 2.46 gigahertz at negative 3 dB, and for the attenuation dB we have negative 35, but we get 3.24, so the value of frequency is less than the actual frequency. So after we optimized, we get the actual value. So we get 2.5 gigahertz at negative 3 dB and 3.5 gigahertz at negative 49. So for the band pass filter, this is the final loop circuit. We have G1, G2, G3, G4 and G5. And for G1, we have parallel inductor capacitor, and this is the series inductor capacitor. So the output, so for the band pass filter output we get 3 dB at 2.6 gigahertz and 2.37 gigahertz. That's all. Thank you.
So hi, my name is Muhammad Asfarizan. So I will present the discussion of our RF microwave filter project. Our objective was to design a microwave filter that meets the required specifications using the insertion loss method. After completing the calculation and ADS simulation, the filter achieved the required performance. For the low pass filter, we selected a Chebyshev filter because it provides a steeper roll off than a Butterworth, although there are small ripples in the pass band. The simulation shows that frequencies below 2.5 GHz passed through with very little loss, while frequencies above the cutoff were highly attenuated. At 3.5 GHz, the attenuation was more than 35 dB, which met the design requirement. Finally, ADS optimization helped improve the filter performance by adjusting the transmission line dimensions so it can